Hey everyone, and welcome back to The Explainer. Today, we're diving into a really fascinating foundational topic: how computers actually clean up messy images. We call this morphology. Now, I know that sounds like a big, intimidating word, but don't sweat it. We're going to break this down step by step so that by the end of this, you'll completely understand how this digital magic works.
Here's our game plan for today. We'll start with a quick introduction to morphology, then look at our main tool, the structuring element. From there, we'll hit the core operations, dilation and erosion, before combining them into composites and finishing up with gradients and top hat transforms. So, let's jump right in.
Part 1. Introduction to morphology and exactly how we go about cleaning up shapes. So, in the world of digital image processing, morphology is basically just a set of rules that we use to change, extract, or clean up shapes inside an image. And we usually do this on binary images. Binary just means the image only has two colors, black and white. The pixels are either a 0 for black or a 1 for white. You can kind of think of morphology as a set of digital erasers and markers that let us fix up the shapes inside those black and white pictures.
Moving on to Part 2. Let's talk about the structuring element, which is basically our main tool here.
We usually just call the structuring element the SE for short. I want you to imagine the SE has a tiny magnifying glass, or like a small template. When the computer looks at an image, it takes this little shape and literally slides it across the whole picture, pixel by pixel. And as it slides around, it checks out the pixels underneath it and makes a decision to change the image based on what it sees.
But here's the cool part. The structuring element isn't just locked into one shape. Depending on the exact problem you're trying to solve, you can totally change your tool. It could be a square box, a round disc, a hollow ring, or honestly, just a straight line. Like if you're trying to find round objects in a picture, you'd probably want to use a round disc. It's all about picking the right tool for the job.
All right, Section 3, Core Operations. Let's look at how we make things bigger and make things smaller with dilation and erosion.
Take a look at this really simple image, represented as a grid of numbers. The zeros make up the background, so that's black, and the ones make up that small square shape right in the center, so that's white. This is our original, untouched image. Now let's see what happens when we unleash our first tool on it.
This right here perfectly illustrates dilation. Check out the before and after. Notice how our original small block of ones on the left has physically grown on the right side. The ones actually expanded to fill up almost the entire grid, making the whole shape way thicker.
The big takeaway here is that dilation is basically your growing tool. It expands the boundaries of your white objects. And why is this useful? Well, it's absolutely perfect for when you need to fill in annoying little gaps or holes in your shape. Imagine you have a scanned picture of some text, but the ink is super faded and the letters are broken. A quick dilation pass will grow those letters and connect all the broken parts right back together.
Okay, but what if we take that exact same starting grid of ones and zeros and we do the total opposite? Let's take a look. Enter erosion. Instead of growing things, erosion shrinks our original block. It literally peels away the outer layers of the ones. If you look at the right side, almost all the ones are just gone, and we're left with only a single, tiny one right in the very center. The shape was completely eroded away.
So just remember this simple rule. Erosion is your shrinking tool. It makes the boundaries of your objects smaller. And this is incredibly useful for wiping away tiny speckles of unwanted noise. For instance, think of a medical X-ray image that has tiny white dots of dust or camera noise all over it. Because those noise dots are so small, a single pass of erosion shrinks them down to absolutely nothing, leaving you with a totally clean image.
Section 4, Composites. You've mastered the basics, growing and shrinking. This is where we combine those two tools to do some really cool stuff.
Our first composite tool is called opening, and the formula here is beautifully simple. It's literally just a two-step process. Step 1, you apply erosion to the image, and step 2, you immediately apply dilation to that result. So basically, you shrink it and then you grow it.
Now, why on earth would we shrink something just to grow it again? Well, by shrinking it first, you completely delete those tiny speckles of bright noise forever. They just disappear. Sure, your main object gets a little smaller too, but that's where the second step comes in. The dilation step grows your main shape right back to its normal size. So you get to keep your main shape exactly as it was, but all that annoying noise is completely gone.
Our second composite tool is called closing, and it's the exact reverse of opening. For step 1, we dilate or grow first. Then, for step 2, we apply erosion, so we shrink it. Grow it first, then shrink it.
So what does closing actually do? By growing the shape first, you're building a bridge over any dark holes or narrow cracks inside your object, filling them in completely. Of course, now your object is a bit too fat, but the second step, the shrinking, brings those outside borders right back down to their normal size. You're left with a perfectly solid shape, no holes to be found.
And finally, Section 5, Gradients and Top Hat Transforms. Let's see what happens when we use some basic subtraction to find edges and hidden details.
We call this the morphological gradient, and the formula is just dilation minus erosion. Think about that for a second. If you take a fat, dilated shape, and you literally subtract a skinny, eroded shape, what do you think gets left behind? It's actually pretty brilliant. Dilation gives you the thick version, and erosion gives you the thin version. When you subtract the thin one from the thick one, this simple math leaves you with only the exact outline. It completely highlights the edges of your object. A great real-life example of this is object detection in self-driving cars. If the computer needs to find the exact edge of a stop sign, the gradient operation draws a perfect, crisp outline right around it.
We've also got one more really clever trick, the creatively named white top hat transform. This takes the original image and basically subtracts the opening of that image. It's incredibly good at pulling out tiny, bright details that might be hiding in a badly lit photo. Say you have an image where one side is super dark and the other is too bright. The top hat transform ignores all that bad background lighting and just pinpoints these small, bright objects you're actually looking for.
All right, let's pause for a quick recap, because we covered a lot today. This table right here is basically your master cheat sheet for knowing when to use each operation. You've got dilation, which grows things to fill gaps. You've got erosion, which shrinks things to peel away noise. Then opening is your shrink then grow combo to erase noise while keeping your shape. And closing is the grow then shrink combo to fill in any dark holes.
Before we officially wrap up this explainer, let's try a quick quiz. Which operation removes small bright objects while preserving the overall size of the larger shapes? Take a guess. If you said opening, you nailed it. We shrink to kill the noise and grow to restore the size. So now you know exactly how computers clean up the visual world, from fixing scanned documents to helping self-driving cars stay on the road. And I'll leave you with this final thought. As modern AI models get more and more incredibly complex, how might these foundational, pixel-perfect logic rules hold the key to building vision systems that we can actually trust? Think about it. Thanks so much for hanging out and learning with me today, and I'll catch you in the next explainer.